let's continue today's lesson with the concept stress concentration. Stress concentration. So you may wonder, before we show the definition, you may wonder why for an airplane the window is very small, not like in our house, and the door, as you can see, they don't make a very square, rectangle shape in the corner. It has some round up, etc. And that because that the one of the reason is stress concentration, because if we make the windows for passenger is bigger, then the stress will may concentrate more, and with that it's easy to crack or get the damage to the body of the airplane. And especially something when you design for the door, the entrance for the airplane, the reinforcement surrounding the door is very much, otherwise it may get cracked due to the stress it concentrated on that door. So with that, it's very important to consider how stress concentrate in those change in geometry, it change in the discontinuity. So as you can see here, the material, for example, this is a composite material for the body, and then the change in the geometry here, they discontinue because the door, the window, etc. So it's very important on that. And that is the aviation, but it apply in our civil. Here, something like brittle products for brittle products. It's like you see the concrete, or you see the masonry unit, or you see even stucco. And with the door, as you can see here, the crack, it tend to be go through the corner of the door or at the windows, and that due to the stress also tend to concentrate more on your change in geometry or discontinuity of the material, in this case the empty space for the door, and then the stucco or CMU in there, the cement unit in there. So from that, let me define that, and then we go to into detail. So stress concentration, basically that is stresses as discontinuity, just like window, door, etc. at this continuities, or abrupt geometry change it, abrupt geometry changes, just like from the big size and then go to smaller, that is geometry change that exceed the average stress, the average So for example, when we do the cow member, centric axial loaded member, the average stress is P over A, if you recall that, and that's the average stress. But in this case, because of the discontinuity, the stress tend to concentrate on those discontinuity or the change in geometry that make the stress at that location exceed the average stress that we have. So let's continue with the stress concentration. Continue stress concentration. Continue here. So if we have scenarios in terms of the lines of forces, and what happened for the stress in that case. So if we have a body that continues, no abrupt change in geometry, no discontinuity, then if we have the load P applied, then the line of action of the force, as you can see here, goes straight through the body, Go straight through the body. And that is the load P apply. And that's what they do it in the continuous body. So what stress, if we cut that, go through that body, what happened? Go through that body. If we make that cut, and we have the cut here, and then we have the load P. We have the load P in here, load P. Then the stress on the cut, it will be the sigma average distributed throughout the areas, and that is the sigma average. And that what you already know. Sigma average, for example, for the cow member is P over AT. What if have a discontinuity? With that here, we make a hole in the middle of that body, just like you see the airplane have a passenger windows, so that is the hole, the discontinuity there. So what happened? So if we have the load P apply, for this member, load P, what happened? Just like the you drive on the road, the car, if there is an accident, so that is the hole in here. If we drive another lane, it may not be a problem, but if you drive a lane close to that, it may have some abrupt change in your speed. And if you happen to drive on the lane that go to that discontinuity or the interruption accident, or in this case the hole, then you have to divert, change lanes, right? So exactly the same in here. It have to change lane or change the direction of the force at that. And because of that, it makes the load is concentrated more, because more crowded in that area, as you can see there. Like you change lane in that car because there is a car accident in the middle lane, and that become very crowded in that area. Same with here, the stress will be more crowded in there. So with that, if we cut, make a similar cut, go through that section. So what we will have in here, in terms of the line of stress, what do we have here is and we have a discontinuity, and from that we still have load P, same load. However, I make a metaphor in terms of the traffic flow. You see the load more, the stress more concentrated in that discontinuity, and that we call it is the sigma max. That is changed in here, it become a sigma max. So it really increased compared to the average. So how we can model with sigma max, because sigma max is important, and that you see a concentrate in the discontinuity. That's why if we make too many windows, door for the airplane, there are two ways: you compromise with the safety, or it's very costly to reinforce of those discontinuity. If you see the crack in the civil, normally in some areas that have a hole, discontinuity, or have a change in the geometry of the structure. So with that, let's continue how to model that sigma max, so that we can consider the extra stress applied at those locations. So with that, we go to the next one, is the stress concentration factor. Stress concentration factor. So what does that mean? It have sigma max. We know sigma average. So how can we determine the sigma max? So basically, the stress concentration factor, it represented by K, and it equal to sigma max, the maximum sigma stress over the average stress on the cross section, and that we have it in there. If it no in this case no discontinuity, is sigma average. If there is a discontinuity or the hole in there, sigma max, so that ratio sigma max over sigma average we call it stress concentration factor. And this K, it depends only on the geometry, not the material. Regardless of type of material, that K is still the same for the same time of load with the same time of the discontinuity. So let me write down here. It depends on geometry. Make it now here geometry. So and not material. So regardless of which material, if you have the same hole for the same shape, then the K will be the same. So how can we determine K? That is the next question, right? So how to determine K is determined in a lab. So set up that way with the different common geometry changes, and we want to measure the tension stress in those location with discontinuity or geometry change. So for common geometry changes, geometrical changes. For example, what are the geometry change that we want to look at here? It will be hole or fillet or groove. So those are the geometrical changes that we want to do in the lab and to find out K. And K also depends on the time of load, not material. K depends on type of load. What type of load we are normally consider? For example, axial load or torsion that we will go into discuss in this semester as well. Torsion. So basically that is a torque, a moment, torsion, bending moment. Okay, so those are the factors that we have when we consider the K. Geometry, changes, time of load that we have. So why K is important, especially in certain scenarios. So let's see, K is critical in two scenarios in the design of two scenarios here. The first one, the members composed of brittle material. Do you recall what is the brittle material? So member composed of brittle material. So material, what is the measure the brittleness of material? Recall lesson 3, mechanical properties of materials. When the rupture strength is small, the material with the rupture strength epsilon r very small, that we call brittle material. Concrete, stucco, all of that. cast iron. And with that, as you can see, for example, this one, stucco or cement for the gold. And this one is the brittle material. It tends to, when you design, focus on the stress concentration even more in that scenario. The second scenario that we want to consider, the member subjected to cyclic load. Cyclic loads. The loads that apply over and over again. What is that about in civil? What is that about in other information, in other industry? Let me give you one example for cyclic load that we go earlier here. That the airplane, as you can see, they take off and landing, take off and landing. One airplane can have multiple time during the day, and that apply over and over, years by years, until it retire, the airplane retire, and that is cyclic loss. And that tend to, the stress concentration have to even consider more, and that's why you see application with here that try to limit the number of discontinuity on the airplane body, try to make it small so that it less effect of the K, stress concentration on your small hole, and make a reinforcement in that hole. That is the cyclic load. How about the in civil engineering? What type of structure is that? So if you have the structure like a bridge, you have a cyclic load. The truck, the trains go back and forth, and that will have a cyclic load in there. Or the roller coaster structure, load off on, that is cyclic load. And let me give you example from the book that use different K, how to put the K in here. So for example, in this K, stress distribution near the circular hole, and with the K at here, so what is, they depend on the dB, the depth, big depth, D capital, and then the small d, as you can see here, with the hole and the radius of the hole. And what you need is to find the ratio 2r over d capital in the horizontal, and with that, with the geometry, you just go back to find out the K on the vertical, and that you can determine the maximum stress on the hole. Similarly, if this is the change in geometry, as you can see, that is a rough change in geometry from the with the member from the D capital to a D small depth, and that chain become a fillet in there, and with that you see the sigma max apply in there, and with that sigma max it depends on several factor that you have. The first one is the ratio R small, the radius of the fillet, how that curve is, over D small. We see the small depth of the two, and then the other factor is D capital over D2. For example, if it D capital over D2 equal to 1.5, 1.3, 1.2, so they have different curve, and then you make those two ratio, radius of the fillet of the chain over D small, and then D big over D small, D capital over D small, and then with that find the correct curve, and then find out the K. When K, apply the equation K equals sigma max over sigma average. You can find out the maximum stress at that discontinuity or that change in geometry. With that, we finish the stress concentration factor, and let's go ahead to practice worksheet 4E.